Hello, y'all. Welcome to lesson 96 in my DP chemistry curriculum. Today we're going over reactivity 3.1.4 and 5. So in 3.1.4, we're going to talk about the pH scale, how it can be used to describe the concentration of H plus ions of a solution. We use the equation pH is equal to the negative log base 10 of hydrogen ions, or we can inverse and say hydrogen concentration of hydrogen ions is equal to 10 to the negative pH power. So we'll be able to perform calculations involving the logarithmic relationship between pH and the concentration of hydrogen. In 3.1.5, we're going to talk about the ion product constant of water Kw. It'll show an inverse relationship between H plus and OH minus concentrations. We'll use the equation Kw is equal to the concentration of H plus times the concentration of OH minus. Again, this is also in your data booklet. We'll be able to recognize solutions as acidic, neutral, and basic from relative values of H plus and OH minus. So all those equations are in our data booklet. We'll kind of go over what they are and how to use them. So starting out, we're talking a lot about pH, which most students generally know it's kind of like a scale of acidic or alkaline. Now, alkaline is just a fancy word for basic, either or. But what does pH really mean? Well, pH literally stands for the power of hydrogen, because we're talking about the power of hydrogen ions. You can also sometimes refer to it as potential of hydrogen, but I prefer power of hydrogen. Same thing. Now, so we just use it to determine whether something's acidic or basic. The scale goes from 0 all the way to 14. On this scale, we generally think of 7 right in the middle as neutral. And over here we have acidic, and on the right we have alkaline. So the lower the number, the more acidic it is. Now, it's once again a measure of hydrogen concentration. And hydrogen concentration is what makes something acidic. So it's kind of odd that the zero end is more acidic, meaning more hydrogen. But we have to understand that the equation for pH equals to the negative log 10 of our hydrogen concentration. So as our hydrogen concentration increases, the value for pH will decrease. And once again, we can always inverse this. So if we have our concentration, or if we're looking for a concentration of H plus and we have our pH, that's just equal to 10 to the minus pH power. And that's just transforming the logarithm. So right here, we realize that our scale is inversed. A higher hydrogen concentration means a lower uh, value on the pH scale or more acidic. Furthermore, one final addition to this is that when we think about H plus, what we're going to realize is H plus is inverse to OH minus concentration. And we're going to prove that a little later. But when we think of something like water, H2O, H2O has equivalent concentrations of H plus and OH minus. And that's pure water with a pH of 7. Those values are exactly identical. And as we look at it in that light, when we think about acids, what we want to think about is a pH less than 7. And we want to think about a concentration of H plus greater than a concentration of OH minus. Conversely, when we're thinking about bases or alkaline solutions, we'll have a pH greater than 7. Those two symbols don't look great together, and a concentration of H plus that is less than the concentration of OH minus. So this is kind of what we're referring to, and we're going to go ahead and actually explore this mathematically in a little bit. But before we talk about OH mathematics, let's talk about pH calculations. So when we look at pH calculations, we'll remind ourselves of that equation, negative log 10 of our H plus. And we'll notice that this is, again, a logarithmic scale base 10. What that tells us is that as the scale increases, scale increases slash decreases, it's a factor of 10, meaning that a pH 2 is 10 times the H plus concentration of pH 3. So pH 2 will have 10 times more hydrogen ions than pH 3 because it's logarithmic. So that's something we're going to keep in mind as we do our calculations. So let's go to our first example of this video slash our only example for this part. We'll calculate the H plus concentration of, or sorry, not H plus concentration, that's inverse. Calculate the pH of a solution with concentration of H plus equal to 0.020 mole decimeter cube inverse. Now, when we do this, we're just going to plug it into our equation. pH is equal to the negative log base 10 of 0.020. And when we plug that in, we find that our pH is approximately 1.70. And so that's it. That's all you really have to do to calculate pH. We could do the inverse, where if we have a 1.7 pH, we could plug it into H plus concentration is equal to 10 to the minus pH, and we would just get the same number right here, 0.020. All right, so that's how we use the equation. It's literally just plug your values in. So what else do we do when we're talking about pH? Well, we often use things called acid or base indicators. So indicators do exactly what they say. They indicate presence of acid or base, but they do it through color change. Indicators are usually going to be qualitative, meaning they'll just tell you whether something's acidic or basic, but we'll discuss that a little bit more in just a moment. One of the common types we'll see in labs is litmus paper. This is probably the most generic qualitative acid-base indicator. We kind of use it like we use phenolphthalein, where if it's red, whoops, if we see red, it's an acid. So you'll have blue litmus paper that turns red, which shows you it's an acid. If it's red and it turns blue, it's a base. And that's pretty much it with the litmus paper. It's a very simple qualitative measurement. Qualitative. We have better indicators, such as universal indicator. Universal indicator is a combination of multiple indicators. And because of that, we can get a little quantitative. I'll say semi-quantitative, where you get a color scale, or a rainbow to represent pH. So you just have to match the color that your solution turns to some type of bar graph that tells you the pH of a solution. And you just play a matching game to figure it out. You get a spectrum of color for that. There are many other indicators that are similar to universal indicator, where they change under certain ranges, so they can help you identify what pH something is around. But usually universal indicator is one of the best for just a semi-qualitative. It's about a pH of 3 or 3.5. All right, so that's indicators. The last thing that we're going to talk about here in this video is called the ionic product of water. So when we think about water, and I kind of foreshadowed it earlier in this video, uh, water is generally stable. Water is stable. Pure water has no ions, or seems to not have ions. And we know that because it does not conduct electricity. But it kind of does, actually. That's the weird thing. It actually dissociates slightly. And it's a very, very small dissociation. When we look at water, it can break down in an equilibrium to form, oops, this is a chemical reaction, H plus aqueous plus OH minus aqueous. So it can break down to form kind of like its acid-base components. It's creating H plus and creating OH minus. Now, we know water doesn't just do this often because our pure water is, again, not conductive. And so we know for the most part it is in this state, meaning that if we were to do a Kc or calculate the equilibrium constant, we know our equilibrium constant is going to be far less than 1. Well, with water, instead of calling it Kc, we actually call it Kw, so the equilibrium constant for water, and we can just calculate it by taking the concentration of H plus, multiplying by the concentration of OH minus, and we divide it by nothing because water is a liquid in the reactant stage. So this equation right here is what we actually call our ionic product of water. And it's called that because it's the product of the concentration of ions. It's a simple name for exactly what it is. We mentioned earlier that pure water has a pH equal to 7. And we also said our concentration of H plus and OH minus are the same. Well, it turns out our concentration of OH minus and our concentration of H plus, which once again are the same, is 1.00 times 10 to the minus 7th mole decimeter cube inverse. So because of that, we can now calculate the ionic product of water as just 1.00 times 10 to the minus 7th squared, as our H plus and OH minus concentrations are equivalent, which means it's 1.00 times 10 to the minus 14th mole squared decimeter to the 6th inverse. And that is the actual representation of our ionic product of water. We can now look at the relationship between H plus and OH minus by using the ionic product of water. As our H plus decreases, our OH minus will increase to continue to exist at this concentration or at this product. Again, now as our H plus increases, our OH minus will decrease. So these are inverse. These are inverse relationships. So we can say as concentration of H plus increases, OH minus decreases, and vice versa. And this helps explain the pH scale. If OH is representative of our base, we need to have a lot of it and very little H plus to go to our alkaline side of our pH scale. On our acidic side of our pH scale, we need a lot of H plus and very little OH minus. So this relationship makes mathematical sense as well as just general logical sense with what we know about acids and bases. The last thing we can do is now use our ionic product to calculate both H plus and OH minus concentrations. So we'll do our last example problem. We'll say solution has pH equivalent to 3.20 at 298. I give this temperature 298 because, as we mentioned before, this is a equilibrium constant. And as such, it's going to be temperature dependent. Temp dependent. And this is only true at 298 Kelvin. So for our first example, we're assuming 298 Kelvin. To solve for H plus, we learned that earlier. It's just 10 to the minus pH, which is equal to 10 to the minus 3.2. When we plug that into our calculator, we get a concentration of 6.31 times 10 to the minus fourth mole decimeter cube inverse. And that is our H plus concentration. Our OH minus concentration, we now have to take our ionic product of water as the concentration of H plus times the concentration of OH minus. We can plug in the values we know, but first I'm going to do a little rearranging. I'll take OH minus is equivalent to the ionic product of water divided by the concentration of H plus. Now I'll plug in my values, getting 1.00 times 10 to the minus 14th divided by 6.31 times 10 to the minus 4th to get my concentration of OH minus as 1.58 times 10 to the minus 11th. And that will be in moles decimeter cube inverse because we originally had moles decimeter cube inverse. We're dividing our actual mole squared decimeter to the -6 inverse by that value, providing us with our final answer. So all you should really be able to do is use the ionic product of water to calculate OH minus and H plus, as well as use these equations we took at the beginning. The pH is equal to the negative log of H plus, as well as our other equation right up here. H plus is equal to the negative 10 to the negative pH. I hope this helps you get ready for your calculations with pH and have a great day.